Hello everyone. Thank you for joining my presentation today. My name is Sung-eun Hong and I'm here to present a paper titled ParCo, Part Coordinating Text Motion Synthesis. This work will be presented at the ECCV 2024 conference. The paper introduces a novel-made approach to text motion generation, which I will walk you through in detail. We will explore the foundation techniques, the improvements brought by ParCo, and its performance compared to other models. Let's get started. First, let's define text motion generation. This process involves creating realistic human movements or animations based on text descriptions. It's challenging task because we are translating natural language, which is inherently ambiguous, into precise, coordinated human movements. Imagine describing a dance move or an athletic movement in words. Every detail, such as speed, direction, and rhythm, must be captured. The system needs to interpret this natural language input and generate motion data that reflects the provided descriptions. For example, in the first image, the character takes 4 steps backward. In the second image, the character is running on the treadmill. In the third, the character performs a kick spin to the left. Each of these movements is generated based solely on text descriptions, showcasing how the system translates words into corresponding animations. Before ParCo, a lot of text and motion generation models were based on the variation autoencoder approach, which is widely used in generative models. The VQVAE works by encoding input data into a compressed latent representation and then decoding it to generate an output. In the case of motion generation, the input could be a textual description, and the output is the corresponding motion sequence. T2M and TEMOS are two well-known models that use this VQVAE architecture. T2M, for instance, focuses on generating diverse and natural 3D human motions based on text descriptions. Similarly, TEMOS works on generating diverse motions from textual input. As shown in the diagram, the encoder captures the latent variables, which represent the key feature of the input data. The decoder then reconstructs the motion based on these latent variables. The advantage of the VQVAE is that it can produce a variety of motion outputs from the same text input, but diversity can sometimes come at the cost of precision. Another important approach to text-to-motion generation is the diffusion model. Unlike the VQVAE, the diffusion model starts by generating random noise and then refines this noise over time, slowly converting it into a coherent and realistic motion sequence. Each step of refinement brings the motion closer to the intended result, as described by the input text. Two key works using diffusion models are MDM, which was presented at ICL 2023, and MLD, introduced at CBPL 2023. The diffusion model process can be likened to sculpting a figure from a block or marble. You start with rough shape and gradually refine it until you reach the final detailed result. This method has been shown to produce high-quality, smooth animations that closely align with texture descriptions. Next, let's discuss the vector quantized variation autoencoder VQVAE, which builds on the transitional VAE by introducing a codebook. In this model, the codebook allows the system to map text to specific motion codes. These codes represent discrete segments of the motion, which makes the entire process more efficient and structured. This is a key difference from standard VAEs, where the latent space is continuous. Works that use this architecture include MoMask, which focuses on generating masked human motion in 3D, and ParCo, which I'll discuss in more detail shortly. As you can see in the diagram, VQVAE encodes the input motion into a series of discrete codes. The decoder then uses these codes to generate the final motion sequence. This discrete represent allows for more efficient training and generating, as well as higher precision in the resulting animations. Let's now dive into one of the key aspects of this paper, the part-based method. The part-based method divides the body into different segments, such as arms, legs, torso, and head. The idea is to generate motion for each part separately, which offers more control over each part's movement. Once the motion for each part is generated, these parts are then combined to form the full body motion. This method is particularly useful when dealing with complex motions that involve multiple parts of the body moving simultaneously or in coordination. For example, think about dance moves, athletic performance, or martial arts sequences. By generating each part separately, you can achieve much finer control over the details of each movement. While the part-based method provides precision, it also introduces some challenges. Coordinating body parts that are generated separately can lead to problems. If the arms and legs are not synchronized properly, the overall motion may appear unnatural. For instance, a small misalignment between the movements of the arms and legs can make the entire animation look awkward or robotic. Additionally, managing and synchronizing these parts adds computational complexity. The more body parts you're generating, the harder it becomes to ensure that all of them move fluidly and naturally together. This is especially important for complex actions like a head spin or backflip, where multiple body parts are moving in coordination. To solve the issues posed by the part-based method, ParCo was introduced. ParCo addresses these challenges by using lightweight generators for each body part. Each body part, such as the arms, legs, and torso, is generated separately, but ParCo was introduced a coordination module to synchronize these parts. This ensures that the entire body moves smoothly as a whole, without any awkward or jerky transitions between the different parts. By synchronizing the body parts during motion generation, ParCo achieves a higher level of realism while keeping the computational requirements manageable. This allows it to generate realistic full movements efficiently. Now, let's take a deeper look at the architecture of ParCo. ParCo is built on T2M GPT Foundation and combines the VQVAE architecture with an autoregressive model. It independently generates motion for 6 different body parts: the right arm, right leg, and torso and glute. In the diagram, you can see how the model breaks down full motion into these separate parts. Each part is processed through an encoder, and then all parts are synthesized into single, coordinated full-body motion. This modular approach allows ParCo to handle complex movements with precision. The PartCoordinated Transform is the core of ParCo's architecture. Each body part has its own dedicated transformer, and the part coordination layer ensures that these transformers are synchronized. This layer allows the different body parts to share information with one another, making sure that the arms, legs, and other parts move in harmony. Without this layer, the generated motions could look disjointed or unnatural. The part coordination layer plays a key role maintaining fluidity across the entire body. Let's now look at the dataset used to evaluate ParCo. The first is Human ML3D. Human ML3D combines the Human Act 12 and AMAS datasets. It includes 28 hours of motion data and consists of 14,616 individual motions paired with 44,917 descriptions. These text descriptions are detailed enough to map directly to specific human movements. For example, a description like a person raises their left arm above their head corresponds to precise motion sequence. This dataset is ideal for training and evaluating texted motion generations models like ParCo. Another important dataset is KitML. KitML includes 3,911 motions totaling 11 hours of data, along with 6,278 natural language annotations. These annotations contain over 52,903 words, making it a rich source of diverse motion descriptions. This diversity makes it possible to evaluate how well the model can handle a wide range of motion descriptions. To evaluate the performance of ParCo, several key metrics were used. Precision, which measures how well the generated motion matches the text input. FID, which qualifies how similar the generated motions are to the real ones. Multimodal dist, which reflects the semantic similarity between the text and motion. Diversity, which measures the variation in the generated motions. Multimodality, which assesses how varied the generated motions are for the same text input. The result of the experiment showed that ParCo outperforms other models across metrics, especially in FID. ParCo achieves higher scores for both the Human ML3D and KitML datasets, producing more accurate and semantically aligned motions. This indicates that ParCo is more effective at generating motions that match the text input, providing both accuracy and variety. Another advantage of ParCo is its computational efficiency. It uses fewer parameters and fewer flops compared to models like Remote Diffuse and T2MGPT. Additionally, ParCo's inference time is much faster, making not only accurate but also higher efficient in terms of resource usage. In addition to quantitative research, this paper also performed a qualitative comparison to see how ParCo performs in real-world scenarios. In the examples, you can see the ParCo generates more realistic and accurate motions compared to the other models. For example, in a sequence where a person stands back, picks something up, and places it on their head, ParCo captures the full sequence accurately. Other models, however, tend to miss certain actions or generating incorrect movements. In conclusion, ParCo presents a novel approach to text motion generation, overcoming many of the challenges associated with earlier models. It provides precise, realistic, and computational efficient solutions for generating complex human movements based on texture description. Thank you for all your time. If you have any question or would like to discuss the work further, feel free to reach out to me. Thank you.